doing cosmology with machine learning using LSST. So take it away.
Yeah, thank you for having me. I am Irene Moskowitz. I'm doing my PhD thesis in my final year with Erica Weiser at Rutgers. And I'm mostly going to talk about some problems with redshifts for LSST and how we can maybe solve them to get better cosmology. So this is a cosmology talk. I'm legally required to show this diagram.
You should not bring that diagram to this room because we'll start asking you to explain why you really believe those fluctuations are quantum.
Well, I'm not talking about those fluctuations anyway. We're focusing more on this end of the diagram. Basically, galaxies and dark matter halos are forming as the universe is expanding. That expansion is pushed in part by dark energy, which is now the dominant component in our universe. And so because galaxies are all forming in this context of dark energy, we can use galaxies to learn about dark energy. That's the short version of this proof that I hope you'll believe. So a brief outline. I'll start on some background, talking about the two probes that I focus on for cosmology with LSST, which are galaxy clustering and weak lensing. I'll do a brief interview to the Rubin Observatory and some really exciting things about it. And then I'll talk about what a photometric redshift actually is and some associated problems with photometric redshifts before talking about various things I have attempted to try and fix some of those problems. And then we'll conclude on hopefully a slightly sunny note. So to start, galaxy clustering is the main probe that I focus on. So we want to probe the overall matter power spectrum. Galaxies form in dark matter halos. We care about all of it, but since galaxies form in dark matter halos, they are a biased tracer of the total large-scale structure. So basically, the galaxy density fluctuations are related to the total matter fluctuations by some bias term. And then in this figure over here, every blue dot is a galaxy. So you can see that there is some structure to the way that galaxies are distributed throughout space. It's not uniform, so and that structure is related to the cosmology that we care about. So dark energy is causing the universe to expand, and so the rate of that expansion will determine what scale this clustering happens on, and things like that. So that's galaxy clustering. We also have weak lensing, which is maybe slightly less exciting than strong lensing, because we don't get as many really cool giant arcs or multiply imaged things. But weak lensing just slightly distorts the shapes of the galaxies that we observe on the sky. And this is because as the light from source galaxies travels through the large-scale structure to reach us, it's getting slightly lensed by everything that it passes through. So weak lensing is sensitive to all of this matter, so we don't have to worry about galaxy bias in this case because we're seeing all of the stuff is influencing this. But it is a statistical probe. Right? We cannot see the difference between an unlensed shape, and even so this diagram is greatly magnified, the effect. But we do not know when we look at a galaxy what the intrinsic shape was. And we also have to worry about the fact that galaxies forming in the same environment will also have some intrinsically aligned shapes. So we want to look at the shapes of all of the galaxies in our sample, and then we look at statistically how similar are those shapes in different regions of the sky. And that will tell us something about the lensing, which is coming from the structure, the large-scale structure, but there's also this intrinsic alignment you have to work out. But the correlation of the shapes, differently from random, also tells you about the large-scale structure. So the 3x2 point method is a combination of this galaxy clustering and weak lensing. Like I said, galaxy clustering has galaxy bias, which weak lensing does not have, but weak lensing is sensitive to intrinsic alignments, which galaxy clustering doesn't care about. So there's there's different systematics for each probe, and so they can they're very complementary. And if we combine them, we can get tighter constraints on our cosmology. So to sort of illustrate what the 3x2 point method looks like, I have my two cats, Schrodinger and Obsidian. So for galaxy clustering, this is the 2-point autocorrelation between galaxy locations at different angular scales. So you'll count up for some separation angle how many pairs of galaxies in your sample are at this like small separation angle, how many of them are at larger separation angles, and for each, you'll bin your separation angles and you'll count up for each set of separation angles, how many pairs of galaxies do you have? And then you will compare that to if you just had a random distribution of galaxies, there would also be some, you'd have some clustering like that. And then the difference between your random and what you actually measure is your galaxy clustering, 2-point correlation function. Cosmic shear is this weak lensing. So this is where you have, weak lensing has sheared, changed the shapes, intrinsic shapes of your galaxies that you observe. And so you will count up again for your different separation angles, how correlated are shapes at small separation angles, how correlated are shapes at larger separation angles, and you'll count those out. And then again, you would expect if there was no cosmology, you'd have some random, and you had some random distribution of galaxy shapes, you'd still have some signal. So the difference between this correlation that you measure and random is now your cosmic shear, 2-point correlation function. And then you can also do the cross correlation between the two. So this is called galaxy-galaxy lensing, where it's just at a location you'll have some galaxy at some, the galaxies at some separation angle from that galaxy. How correlated are the shapes with each other? So small scales, again, large scales. So you can do that on all of your size scales, and that is galaxy-galaxy lensing. And so this actually helps you, the galaxy-galaxy lensing and the galaxy clustering helps you measure that galaxy bias, because each correlation function has, for galaxy clustering, you have two factors of the bias, because you have two galaxy clustering fields that you're correlating. Galaxy-galaxy lensing only has one factor of bias, so this is just one example of how you could start to disentangle these extra confounding factors, nuisance parameters, by combining the two probes. Okay, so this brings us to LSST and the Vera C. Rubin Observatory. So this is the legacy survey of space and time, which I am now very excited to say has seen first light in the past this spring. So that was very exciting, and it is still forecasted to begin actual survey operations this fall. So that's also very exciting. But the LSST consists of the 8.4 meter Simone Survey Telescope, which is equipped with the LSST camera, which is in the Guinness Book of World Records as the largest digital camera ever built. So LSST will observe the entirety of the southern hemisphere sky over 10 years, and it will cover the whole sky every few days. And it's expected to observe tens of billions of galaxies, hundreds of thousands of supernovae, stars, asteroids, comets. It's great for all kinds of science, but I'm really excited about the cosmology aspect. So all of these tens of billions of galaxies will bring unprecedented data volume for this 3x2 point method. But unprecedented data volume also brings unprecedented challenges. And one of those is doing redshifts. You need a redshift. If you want to measure this galaxy clustering or weak lensing, for example, over cosmic time, you need a redshift to place it in order. And the best way to do that is with spectra, right? So you get your galaxy spectrum, you find sort of known features like maybe this O3 line or this H alpha line, and you compare the observed wavelength of those features with what you know it is intrinsically, and then that will give you the redshift. This is very accurate, but they require long observing times, and it is not feasible for on the scale of tens of billions of galaxies. It's just not going to happen. So we have to use photometric redshifts instead, which are a little bit trickier. But the idea behind photometric redshifts is that if you take, so here we have the LSST filters and just a sample galaxy spectrum, and as this spectrum moves through the filters at different redshifts, you can see that the amount of flux that you will get through each of those filters is changing in a predictable way. So there is some intrinsic relationship between your photometry and your redshift, but this is also tricky because there are some degeneracies there. But it is predictable. So there are two main methods that we can use to get a photometric redshift. The first one is template fitting, which is probably the most intuitive. You have some library of sample spectra that you can redshift on whatever grid spacing you want. You know what your filters are, so you can, for each spectrum in your library, at each redshift in your grid, you can generate what the photometry would be of that galaxy, and you can compare that to the photometry of the galaxy you're trying to estimate a redshift for. You do some chi-square fitting, find the best fit, and you will get out your redshift. This is great. There's no black box. You know exactly what's happening. You know exactly why you're getting the redshift estimate that you're getting. But it doesn't scale very well with large data sets because you have to do this whole process for every single, for every single galaxy in your sample. And if you want to get redshifts for tens of billions of objects, that will take a very long time. So machine learning is a way to speed this up. It's scalable. You just learn a relationship between your training sample. In your training sample, you can learn what the relationship between photometry and redshift is, and then you just apply that to all of the galaxies in your sample basically at once. It takes a much shorter amount of time, but it requires a representative training sample to work well. If you want to estimate the redshift for a galaxy that has photometry totally different than anything you trained your model on, it's not going to know what to do with that galaxy. And as I will show in a little bit, we will not have representative training samples for LSST.
Can I pause you there?
Yes.
If I were giving this slide, I would have said that the big problem with template fitting is that the templates are wrong.
Yes, there's also that.
But you didn't, that's not what you led with though. Is that because you are in the end going to rely on the templates in some sense? Or are you going to be able to train without ever touching a template?
So we can train without using templates at all.
Because you have some galaxies at different brightness levels for which, through some clever tricks, you know their redshifts.
Yes. Yeah. So my work does not use we're not using templates at all in any way.
At all. So you never use templates. Good. Because it feels to me like if the only issue was speed, I feel like we could do it. If I had a grant and we had 10 billion galaxies, I think I could do template fitting on 10 billion galaxies. I mean, the Gaia team did a harder thing with that on 2 billion stars.
Yes. For the purposes of this talk, the speed is the main limiting factor because we're not using templates. But yes, especially at high redshift 2, the templates are also, we are not confident in the templates anyway.
Yeah, good. I'm just saying that I think that's a stronger, like intellectually, I think it's a stronger argument because I think if we had to do the template fitting for 10 billion galaxies, we'd find a way.
Yeah, I think, so template fitting, from what I'm remembering, it works decently well for at least simulated LSST galaxies. I know people are using it to do various testing things.
But in simulated cases, you do know what the galaxies are made of.
Yeah. So,
but anyway, stay on target. I just wanted to check in.
All right, so we're going to go through a little exercise to illustrate how bad this non-representativeness could be for photoz's. So I'm using simulated LSST data because at the time that was all that we had. We did not have real LSST data. I'm using the DC2 catalog, which was made by the Dark Energy Science Collaboration, which I'm a member of, basically to test all of our pipelines in preparation for real Rubin data. So I will start with, as a baseline, the ideal case. We have a fully representative training sample. So from this DC2 catalog, I randomly selected 200,000 galaxies to be our training. I randomly selected 5.5 million to be our application sample. This is what we're estimating redshifts for. I used the FlexiBoost code for doing my photoz estimating. You could have chosen any number of things. I went with FlexiBoost. It worked mostly the best. And so the results are in this top plot over here. We have the true redshift on the x-axis, the photometric redshift on the y-axis, and those solid black lines are the outliers. So you can see almost everything is basically on this one-to-one line. We get the photoz, it's pretty much the same as the true z. This seems like it works great. We've got this kind of like feature up here, which is about the degeneracy. There's some color redshift degeneracy. So we will never fully be able to make that go away with machine learning. It's just inherent. But it works really well. We have about 14% outlier fraction for this just quick little demo. Most of that is, again, coming from like this degeneracy that we know about. But what happens if we make this more realistic? So now, instead of this 200,000 randomly selected galaxies for a training sample, I have used created a training sample that mimics the properties of HSC galaxies that have matched spectroscopic redshifts. So this looks like, HSC is the closest photometrically to what LSST will be. So it looks like an existing spectroscopic sample that we have. There's a color magnitude diagram right here of this new training sample. This is the same application sample that we had before. And you can see that, so this region where most of our training galaxies is like down here. And this kind of where the bulk of our galaxies we want photoz's for is right here. So there's nothing there in our training sample. And if you redo this whole photometric redshift estimate, this is now what you get. So it's okay up to about redshift of 0.8. That's what's in our training sample. After that, not only do we have a large outlier fraction, it's pretty catastrophically bad. It's the 50% outlier fraction. This is terrible. You cannot do precision cosmology if half of your sample has a catastrophically bad redshift estimate.
Is 14% before that looked okay? Is that good enough for doing cosmology?
It's not ideal. I mean, this is like not how we're actually going to estimate redshifts.
Okay.
For like the Dark Energy Science Collaboration. It was mostly just did this to be, illustrative of what could go wrong. Yeah, but there are ways that you can calibrate out that kind of that feature.
Like anything based off of the photometry, anything with that photometry just cut out from the sample. Or?
Yeah. So you can do photometric cuts. You can also do if you know what your sort of if you have a spectroscopic sample and that you can sort of look at the distribution of your spectroscopic sample and you assume that your photometric sample is probably similar, you can calibrate out some of these differences.
Can I make you shouldn't bring a plot like this to this room because it's going to be hard to get to your next slide. One thing is, why did your outliers at the left edge outliers go down when your training sample got worse?
Yeah, so this is it's right. So this is at low redshift, it's just kind of not really giving you anything at low redshift in this case.
I see, because it rebalanced the training set somehow in a way that became less important.
Yes, yeah. So
Okay,
there's bigger issues now.
Fine. Second comment is, even in the representative case, there's a bias at high redshift. So, and this is generic in machine learning methods, you'll never get around it. It will always pull the highest redshifts down. So notice, in 2.5 to 3, you just never agree photometrically that it's in that range. And I think that there's an issue here that it might be that even if you get to perfect cases, you're still going to have some biases floating.
Yeah.
Third thing is, in this bottom panel, though you say you do okay below redshift 0.8, you do well below redshift 0.8 in the true redshift. You don't do well in redshift below 0.8 in the photometric redshift,
yeah.
And you'll only have access to the photometric redshift. There's no way to subsample on photometric redshift. You might be able to subsample on color and magnitude to solve that, but you can't subsample on redshift.
Yeah, there's I do have something a little bit later that tries to do a selection to try and pick. Yeah, so we'll get to that.
Yeah.
But yes, that is also a problem.
Good.
That is one of the things that
was driving your research, presumably. Yeah. Good, great.
So we'll get there. All right. So this is a bad problem.
Yeah, we all. Yeah.
I think we all agree this is a bad problem.
Even the upper plot is not super.
Yeah. So the relatively simple idea that we had to maybe try and address this is training sample augmentation. So this is the idea that you can put simulated galaxies into your training sample to cover this region of feature space that you don't in here, that you don't have anything. Adding simulated data to your training is, by definition, going to bias your photo-Z estimates because it doesn't have the true color redshift relation, because if we knew what that was, we wouldn't have to do photo-Zs. But as long as it is less biased than having no information at all, this could be helpful. So that was the question that we wanted to ask. Is the bias that we get, is it still at least better than what we currently have? So we had a couple of, just as a proof of concept, we did a couple of very simple selection criteria. So you can pick dim galaxies. We've got a lot in our application sample that are above this line, not much in our training sample. So we went to a secondary simulation that has a different color redshift because we wanted to mimic the difference in color redshift relation between real data and whatever simulation you wanted to use. So now we go to our augmentation sample and we just pick dim galaxies. You can pick blue galaxies, again, same concept. You can do sort of like a fit if you want to do a joint color magnitude fit to this, to this diagram, and then again pick dim and blue galaxies. Or you can do a redshift cut. So our training sample, there's like nothing above a redshift of 1 in our training sample. There's a lot of stuff above a redshift of 1 in the galaxies we want to estimate photo-Zs for, so just pick high redshift galaxies and add those to your training sample. You can combine that redshift selection with any of these color magnitude, photometric criteria, and you get 7 different ways that you can pick galaxies. So we just added 10,000. We picked a small number, didn't take a lot of work. Add 10,000 galaxies to your training sample using one of these 7 selection criteria. Retrain your photo-Zs and see what you get. And so the big question, does it work? Yes, just pretty simply. So we did no optimization whatsoever of selection criteria, how many galaxies to pick, just simply proof of concept. We already get a 50% reduction in the outlier fraction between this, our best performance augmentation case and the unaugmented is already 50% lower. And if you consider the fact that we're not actually trying to get to 0% outlier, we're trying to get to the representative case, we've gotten 70% of the way back to that. Yeah.
So how do you actually implement the training with the augmented data here?
It's just, you make a new training sample and retrain your model.
So you don't do anything like, I'm thinking of like, there's it's like an example of people doing with like the simulated versus the real is that they'll have like another like input that says like, oh, which class it's from or which data sets it's from, and then it's
no, we haven't done that. We treated them all as if they were all the same.
Cool.
That is something like that you could do, and I will point this out a little bit later for like actually doing cosmology with these. Is to try and, because you don't want to do augmentation at low redshift because you have good data at low redshift. So if you had like a marker, for example, like if you're just doing color magnitude, to say this is simulated, don't use it if you think your photo-Z should be low. Take it out and then redo it. That would be helpful. This was just really simple.
Gotcha.
To see if it worked. Yeah.
What happened at 1.5?
Everybody asks that question.
Yeah.
So FlexiBoost is a conditional density estimator. So even if you don't have a large number of galaxies, if you have a sort of overdensity in your feature space in your training sample, it will tend to preferentially assign galaxies to that redshift. And so since high redshift is one of the features, we have like a slight high overdensity just to make this plot at around 1.5. In our training sample, and so now it assigns a lot of galaxies to 1.5. You can do this same augmentation with other photo-Z methods that don't do it that way, and you still get an improvement. You don't get this line. This just, even with the line, had the lowest outlier fraction overall, which is why I'm showing these results. But yeah, you will see improvement with a wide range of photo-Z codes.
I'm sorry, I have another question.
Yeah.
What is a conditional density estimator? Is this a generative model? I'm sorry, I'm thinking of like I'm too new age instead of traditional statistics.
I don't remember exactly all of the details. Let's see, it's based, so FlexiBoost is based on a code called XGBoost. So it's not just for redshifts.
Sure.
FlexiBoost is just for redshifts. How does it work? I don't know. I'd have to go back and look through the paper. Yeah.
In this, how independent is your fake? You put in fake objects. How independent is your generation of fake objects from the simulated data that you're using? Like, is there?
It's totally different. So we're using, most of it is for DC2, which uses FSPS to generate like star formation histories and SEDs and things like that. For augmenting, we're using the Buzzard catalog, which is doing matched SDSS SEDs to generate SEDs for their simulated like halos. So it's completely different methods.
Good. Right.
Yeah, because we really wanted to make sure in real
because
life.
if you put in the correct answer,
Yeah,
it helps you a lot.
Yeah, it will trivially work if you just put the right stuff back in.
Yeah.
So yeah, we were really careful to make sure that we weren't doing that.
Okay, good.
Yeah, so this is the photoz's. We also, one of my collaborators, Yunhao Zhang, has been working on doing this augmentation selection using self-organizing maps, which is a little more sophisticated than just this like quick color magnitude diagram that I tested. So if you put your, basically, this is your application sample that you want photoz's for. This is your initial unaugmented training sample. You can see there's like a bunch of white space, white holes. So then instead of picking from, he didn't use Buzzard in DC2, but as analogous to what I did, instead of picking Buzzard based on color magnitude redshift, you just pick based on where these holes are, and then when you patch these two together, you get a training sample that looks a lot more like your application sample. So this has worked pretty well. He has his paper out on the archive about a month ago or so. So you can also do it more sophisticated. This brings us to tomographic binning. So we have some better photoz's, but even if we had the best photoz's, it's still not precise enough to do like 3D correlation functions. We still have a pretty large uncertainty on our photoz's, even in that fully representative case. So that brings us to, we have to bin our galaxies, and then you do angular correlation functions between samples within each bin. But if you have to bin, you can ask, how should we bin? And so there's sort of three physically motivated choices that you can start out with: equally spaced in redshift, or co-moving distance, or you could put equal numbers of galaxies in each of your bins. Those are kind of easy to explain. The redshift and equal number are pretty common. Co-moving distance is a little bit less so, but also out there. But there's sort of an infinite number of choices that you could possibly make. And so how do you pick something else? One of these isn't necessarily going to work the best. So some considerations that you can take into account: bins with lower numbers of galaxies will have shot noise, and there'll be Poisson noise. So even though LSST as a whole is not shot noise limited, because we'll have tens of billions of galaxies, you need to be careful that your bins are populated. More bins, you can get more information out of bins, but you don't want them to be so narrow that your photoz's uncertainty is now wider than your bin. So you need to keep that into account. And your photoz's are better at lower redshifts. So maybe you could have narrower bins there where the uncertainty is less, wider bins at higher redshift where the uncertainty is higher. But how do you actually probe all of the possible choices? Like, how do you come up with a different answer?
By the way, I disagree with the point about narrower than the uncertainty. You know that in a spectrograph, we put down pixels closer than the resolution of the spectrograph. If you don't, you're undersampled and you lose information about the spectrum. If you want to transmit all the information from the spectrum, you actually have to have pixels that fully sample the uncertainty in the... You can think of the resolution of the spectrograph as the uncertainty in the wavelength of each photon.
Yeah, so
and you actually want to do finer than the uncertainty. If you don't, you actually sacrifice information. It would be bad.
But I think for the photometric redshifts though, because we're trying to along with this, which I'm not actually going to talk about, you're also trying to calibrate the N of Z distribution of each of your bins. And so you want to, if your bin is narrower than the uncertainty, you're running the risk that your galaxies are actually not in the right bin. And if you have a very high number of galaxies that are in not even like necessarily the neighbor, like they're too narrow. Like if they're in the neighboring bin, that's like kind of okay. You can kind of still calibrate things. But if it starts to get further away from the neighboring bin, then you're running into issues with calibrating your NFC distributions.
I still don't agree with that, but we can discuss it over lunch. I think what you want to do in the end is forward model that with your belief about your photometric redshift distribution, and then more bins is always better. You could even do single galaxy bins, actually. In the cross correlations, you can actually do single galaxy bins.
Yeah, I think that is probably not going to be the fiducial strategy of the dark energy science collaboration.
Anyway, stay on track.
So we introduced this binning equation just as a method of probing possible choices for bin edges. So it's just, it's an integral over features of your sample. So you have what you think your redshift distribution is, some factor of alpha, your co-moving distance, some factor of beta. You integrate that over your photo Z estimates. So this Z max is your photo Z that you think you have. So you can do that for a whole bunch of alpha and beta. You'll get some value for M. Most of the time, M is not a physical quantity. And then you can divide M into however many n equal intervals for n bins. I used 10 for this example. And then you can interpolate between M and redshift to get, to translate your M bins into Z bins, redshift bins. We picked this form of the equation because a couple of choices of alpha and beta will get you back those equally spaced in redshift, equally spaced in co-moving distance of equal number. So we wanted that to be a point of comparison.
Interesting. So you didn't find the binning that transmits the most information about the cosmological parameters.
So that comes into the optimization. So this is just for generating a large
just
number
for generating
of bins.
options.
Yes.
Got it.
And so
Great.
and so then we want to know which of those options is better.
Got it. Understood.
So what we did for that is So we have all these options. We did for this. It's just a Fisher forecasting. If you use those bins, what is your dark energy figure of merit that you would think that you get out of that in the Fisher forecast? And then we maximize the figure of merit to decide which bins we should use. So this heat map is showing, these are our sort of 3 initial ones, and our best case is sort of over here. So it has a similar alpha to equal number and equal redshift, but it's a different beta, it's a higher beta. So there's nothing like physical about these bins that I can really say other than this comparison is our optimized bins compared to the equally spaced and co-moving distance, which was the best of the other 3. And you can see that the bins at lower redshift are narrower, where we have better photo Zs. They are wider at higher redshift. And then that's also why the equal co-moving distance performed the best out of those other 3, because you also have narrower bins at low redshift and wider bins at high redshift. So that's why we think this is happening. So we can improve the figure of merit by a decent amount there. We can also think about sample selection. Tens of billions of galaxies. You could think, well, if you get rid of 90% of tens of billions, you still have billions of galaxies. So if we don't want to get rid of 90% of our sample, but you could try and throw out what are galaxies that have the worst photo Zs. So we trained a neural network classifier to try and do this. What is the likelihood that a galaxy's photo Z is an outlier? So a confidence of 1, likely to be accurate. Confidence of 0, likely to be an outlier. And then this plot is just showing the discard fraction. So light values are close to 100% of your galaxies we're removing for having poor photo Zs. Dark colors are your keeping galaxies. So we're pretty much keeping all of these on the diagonal, and it works better over here than it does over here. But you're getting rid of a lot of the off diagonals in this case. So we're doing for up until about like a redshift of 1 or so, we can be fairly confident in our photo-Z's because we're kind of, we're getting rid of all of this stuff. Again, higher redshift, everything performs worse at higher redshift because that's where we don't have as much spectroscopic coverage. So again, this is also trained with the non-representative training sample because that's what we'll have.
And it decides not to discard Connor's redshift 1.5 feature.
So you also have that.
It is interesting, but I mean, this is a hard ask for the machine learning. You're asking
Yes.
the machine learning to tell you when the machine learning is wrong.
Yeah.
Can't hurt its feelings.
So it works decently well. There are still some issues. It's not perfect. Machine learning will never be perfect. But it works pretty well at identifying galaxies that we think have bad photo-Z estimates.
And this happens on the already trained model that predicts you. It's
Yes.
not a joint train. Okay.
So we train photo-Z's. So we basically have to split our spectroscopic sample into 2. So we have one training sample for the photo-Z's, and then one training sample. We take that model that we learned for the photo-Z's and we apply it to get a photo-Z estimate for now our second training sample, which can now learn the difference. It's learning for like what photometry features give you a good photo-Z estimate and which ones don't. Our training, we have spectroscopic is split into 2, one of them for photo-Z's, one of them you then get photo-Z's, and then that spectroscopic plus photo-Z estimate is now the training sample for your neural network classifier to do this. So if you combine them, this binning optimization plus this neural network classifier, you get a 25% increase in the figure of merit. That's like about an extra 2.5 years of LSST, which is great because LSST costs a lot of money. So we can get more out of what we already have. None of this was cosmology though. We did some Fisher forecasting. We got some redshifts. But we want to know, like, is this actually going to reduce bias in our actual cosmology? So I have some extremely preliminary results. We're still using simulated LSST data at this point, but now we're trying to do some actual cosmology measurements. So I'm using the desk code TX pipe, which is what we developed to do our 2-point correlation function measurements. And then for our 3 different samples for redshift getting photo-Z's, we have the representative, augmented, and unaugmented. This is our galaxy clustering correlation function in each of our 10 bins. So at low redshift, the unaugmented does better than the augmented, which is kind of to be expected because you have good spectroscopic coverage at low redshift. So now you're adding in simulated stuff, which is biasing your photo-Z's, and so at low redshift you actually do worse when you have augmentation, which we expect. So you want to try and figure out a way to make sure that it's not using, this is where having that marked catalog. If we think it's a low redshift galaxy, take out everything that is simulated and redo the photo-Z estimate and see if it's still low. At high redshift, there's not like a huge difference between the augmented and the unaugmented because again, this is where we're still not doing super great, the augmentation. But in the intermediate redshift bins, you can see that there's a large difference in the correlation function for the representative versus unaugmented, and that augmented is now much closer to the representative case than the unaugmented case. So this is sort of like a sneak preview, hopefully that this might be working. And then one last plot.
I'm enjoying the fact that you don't put the truth. You just put representative.
Oh, yeah, so I've actually been having some issues with running the truth value, because our pipelines are not set up to do things with true redshifts.
Yes,
so,
exactly, yeah.
So I don't have that yet, but I am working on getting it.
But it is interesting because it is kind of an empirical baseline, since God will never give you the truth.
Yeah, so we really care about reducing bias compared to like our actual ideal science, which is which is representative photo-Z.
That's an interesting
But yes,
point.
I am also trying
It's like you're not a realist.
fighting with it to make it use real, true redshifts as opposed to assuming that there will be a Photo Z catalog to add that onto this plot. So then we also have cosmology. So this is even more preliminary than the last slide. There's a lot of issues with this plot that probably you will notice. But it's using the desk code Firecrown to do the MCMC sampling on our data vector, which comes from TXPipe, the last slide, to actually get cosmological constraints. So I just have W and omega C, so the equation of state parameter for dark energy and the dark matter density. Color scheme is the same. Again, we have representative in yellow. Unaugmented is over here, so it's pretty biased in both of these parameters. And the augmented case at least reduces bias by quite a bit in omega C, not quite W yet, but I still need to implement a lot of things. So there's scale cuts that I have not used here. I'm only using a very small area of the DC2 catalog just for testing purposes to see, like, make this run and make sure it's kind of doing what we expect. So using the whole area will be more ideal because you can't really do cosmology with 3 square degrees like this. Not sampling over nuisance parameters yet. I'm just W and omega C. Everything else I have fixed to kind of like the input cosmology. But we can already see that there's a decrease in bias, so this is kind of like hopefully in the future this will work. So I'll just leave you with some conclusions. The success of LSST cosmology is crucially dependent on the photo Zs. Photo Zs will be pretty bad if we sort of naively assume that we'll have a representative case, but I have shown that there are some things that we can do to try and mitigate this bias, to reduce and mitigate this bias. Preliminary results look promising. I have a full cosmological analysis in the works. Thank you.
All right, we may have time for a couple questions.
Do you see any evidence? Okay, so long story, extremely long story is SDSS designed and built its own filter system, calibrated it from scratch. I was involved in that calibration. It was very ambitious to build a new photometric system. We then spent a Sondigital Sky Survey learning that photometric system was terrible and we hated everything about it. And then LSST chose in the 90s what filters it would use and froze the filter choice to a set of filters which we knew were terrible. And that's one of the reasons that I've been negative on the LSST project for a long time, because they froze to a decision that we made for totally different reasons a long time earlier and then learned they were bad. Now, you are at the apex of this decision because all of your science depends on these filter curves. Mm-hmm. Do you have any comments? That was a question, by the way.
Do you have comments?
Well, I was 0 to 5 years old in the 90s.
I understand. But it was crazy because you're building this whole new survey. You have the opportunity to do everything from scratch. But they
change the filters.
But which why? Like what? And they didn't. So they chose these filters. Obviously, you now have to suffer with these decisions. They're not your fault. But it is interesting to me. And of course, on your time scale, there'll be something else done with this observatory. So there's an opportunity to do things better. Do you have any feelings about that yet? Or are you avoiding having any feelings about that? Like, it's so critical to your science, right? The exact shapes of these filters. You spend a lot of time thinking about the exact shapes of these filters somehow.
Yeah, so I think as far as like redshifts and filters go, it would have been nice if we had some more infrared, because some of those degeneracies that you get between like color and redshift and also galaxy type and redshift are broken if you have 1 or 2 infrared filters, farther infrared filters. So I think, like, especially at least for calibrating photo Zs, having overlap with like Roman and other infrared surveys in the deep drilling fields is probably going to make or break how well we can do cosmology. So yeah, infrared would have been nice. I have not at this point given a lot of thought to after LSST because I've mostly been thinking about preparing for LSST.
I hate to say this out loud, but you are in exactly the correct career trajectory to be the PI of whatever is next. Right? Like if you just think about, just do the math.
Yes,
whatever's next is going to need a PI. Who's that going to be? It's presumably going to be somebody who's in LSST and who does something important with LSST. So I do actually think it's interesting to think about what to do next, especially since the lead time on LSST was insane. Those decisions were made in the 90s, and it's coming online now. So if we're going to think about what's going to come online 9 years from now, or whatever, 10 years from now, we probably have to think about it now. And you have this huge camera.
Yes.
It's a pretty impressive camera.
All right. Last question.
On the this like technique for synthesizing data, I just at a very basic level am confused as to how you fill in data in a region where you don't have data. How could you like something about the very basic premise of that seems to be deeply flawed. So, could you comment a little bit on that?
I believe I know what they did. You mean the one where they have the self-recognizing map? Is that what you're talking about?
Well, there were multiple techniques of augmenting the data, right? But it was punted to this library, right? The first thing you said, right? I don't know. I didn't really follow it.
When we're doing this with real LSST data, we'll have some spectroscopic sample of real data, and that will be like the base training sample, and that will have it is much easier to get spectra for bright galaxies, for example, than dim galaxies. So we have a lot of bright galaxies with accurate spectroscopic redshifts.
Yep.
We have very few dim galaxies with accurate spectroscopic redshifts.
Z2 is just so few. So,
yeah. And even DESI does improve on this problem, but DESI is not as deep as LSST will be. So there is still going to be regions of we just won't have the spectroscopic coverage, and so. So part of the problem and part of why there is this bias that you will inherently get bias adding in simulated data is because we can only know what the color redshift relationship is where we have spectra, like spectroscopic coverage, and in this region of feature space that doesn't have spectroscopic coverage, we're basically making our best guess, but we're adding simulated data in there.
Right, so you're looking at the small number, is effectively what's happening that you take the small number of high redshift spectroscopic galaxies and be like, okay, here's the color redshift relation, here's properties of these galaxies, and just make more like them, so the machine learning will have more data like that? What's actually happening?
So you could do that, but that's not what I'm doing. It's basically kind of we know at low to maybe intermediate redshift how galaxies evolve, how star formation histories, all of that builds up, and so you can have this library of spectra basically. Depending on your library, they're not necessarily accurate, but it's basically you're using those to generate star formation histories, just simulated star formation histories, which will have. So you'll get a galaxy. If you have, for some star formation history, we'll have some sample of stars in that galaxy, which will be giving off the light. You can make your SED, your simulated SED, based on that. So we're essentially simulating the entire galaxy formation process to make a bunch of simulated galaxies. You can integrate that SED over whatever filters you want. So for LSST, we want these UG RIZY filters, but you could do that for any survey that you wanted.
And then you find objects that from that simulation that aren't represented in your training set, and you put them in.
Yes.
Okay.
Yes.
So it's purely theoretical.
Yeah, okay, this is a far more theory-based than, okay.
It's not what machine learning people call augmentations.
Okay.
What machine learning people call augmentations are where you're like doing manipulations of your data to make more data.
Yeah.
Yeah,
This
that's
is like
what
this
I
is
had
like
thought.
this has I don't know what the name is that's used in machine learning for this.
I feel like it's OD or something. I don't know.
Yeah, when you have
I think
A
they just
mix
call
of-
this more data.
yeah. It's just additional
No, but you're not using
data.
more data. You're using a different data set.
You're
to
just data.
endow it on
But it's,
your-
it's
Yeah.
heterogeneous
It's- no, it's
data
not
training.
source, like,
Yeah.
right?
Yeah.
You could think of it as.
I-
Okay, interesting.
But from an astronomer perspective, augmented is a good word for it because
Yeah.
we do think of it as not data.
Right.
Yeah.
Okay.
I was
Okay.
wondering.
So we do need to stop it here, but so let's thank the speaker again. So here's what's happening.